Well, welcome everyone. It's a pleasure for me to be here and summarize some of the work that I have found especially maybe significant, exciting, and done by just a great group of people whom I greatly admire. Some of them, but maybe not all of them, listed here. There's going to be some amount of detail about our work, but I have maybe three overriding themes here. One, the importance of data, and where I think Sensum's been especially strong in this area. Some of the physical understanding we've gained from the measurements and models, and then some emphasis on who uses the models, making not only our data but the models widely available to practitioners as well as regulators. So Andrew touched on a little of this before, but what temperature? Temperature is one part of thermal comfort that Megan will talk about in more detail later. What you get depends on when and where you are in Singapore. This is a land use map, and we've all traveled around here some and have some sense of the variety of terrain. We've, in our work, have relied very heavily on data that our NUS colleague, Matthias Roth and team, and our research scientist, Eric Velasco, have gathered over a number of years. So this is a world-class data set, and particularly in the tropics. The dots here are temperature sensors, not from government sources, but from Matthias's own network of temperature and humidity sensors, some rain gauges from the government, and then a flux tower here for in a low-rise residential area for sensible and latent heat fluxes and carbon fluxes that we've maintained for many years. And so this is the bedrock by which we validate our models and establish parameters for them as well. So some of Matthias's early work, done about the time, just about the time we were getting started, highlighted several areas, a rural reference in rural undeveloped land used by the military, an HDB area, high-rise residential, low-rise residential, central business district, and this is commercial area. This is kind of Orchard Road, as just exemplars of the places where we have good temperature measurements. And what's come out of that is results that show the temporal and spatial variation of temperatures throughout Singapore. Okay, so these are averages over a diurnal cycle. And the highest are Orchard Road, maybe no surprise, over the year about 4 degrees. HDBs at the lowest. Okay. If we then look, there's a seasonal variation as well with the rainfall patterns. And then some variation just among measurements, and where the biggest peak in that year was a little over 7 degrees. And you look at Orchard Road and you say, well, there's some clue why. It's the anthropogenic heat as one of the factors, in addition to, say, lack of vegetation and building materials that determins urban heating. Okay. So schematically, we say we're, maybe growing up, we say, well, we're inside or we're outside. And in an island like Singapore or in cities, outside isn't really undisturbed outside. We live in a boundary layer, and outside is a product of what we're doing as much as weather patterns at a kind of a regional level. So we're literally down in the weeds. And to model that, we have to account for not only what's happening at the city level, but what is happening, what's forcing it with the local, the regional environment that affects that. So Xianzhang Li and our staff spent about 2 years working with a regional model, WRF, to develop something that I think is still unique in Singapore that can give us, say, island scale sort of average impacts of a lot of effects on the urban heat island. So this is a nested model with five one-way nesting. This is the lowest level here with the commercial areas, low-rise, high-rise residential, and then commercial industrial. The model at the lowest level that determines the energy balance is simply a nodal, say, thermal model with sort of lumped resistances and storage elements in the ground and in walls and communication to the atmosphere above. This is the temperature that's a kind of a construct. It's the outcome of everything else, and this is the temperature in the single-layer urban canopy model that comes out of things. The energy balance here is pretty simple. What are the inputs? If we look at this as a control volume, there's net radiation, shortwave and long wave in minus out. There's us, the anthropogenic heat from buildings, traffic, a little bit of metabolic heat. Where does it go? Sensible heat flux, latent heat flux, and over roughly a diurnal pattern around here, storage in and out of this control volume, including the ground down here. We'll have a little more on the latent heat flux in a minute. That's been particularly interesting. So how big are these terms? And if we look at commercial, industrial, or the other two, the anthropogenic heat, this is watts per square meter of ground area. Here's the net solar, so it's about 100 watts a square meter net. And in commercial areas, the anthropogenic heat is a little more than 85% of that, much less in the HDBs and the low rise. So in commercial, the takeaway is we're putting about as much heat into this control volume as we're getting from solar radiation. So with that understanding, if we look at the plot, revisit the plots that Andrew showed, it's no surprise that for this, the commercial industrial area, the average increment at night of temperature due to our activities and just the nature of the built environment is 2.2 or so. And if we just throw the switch in simulation and get rid of it all, then we're down a little less than half of that. The anthropogenic heat is about half the net solar. Those are the inputs. And if you take away that, you're getting about half of the 50% reduction in the UHI effect. And then there's a spatial variation to this as well that I won't discuss at night and in the day. So this kind of variation is important for the kind of work that Heiko is going to talk about shortly. If we want to look at mitigation of the urban heat island effect, reduction of temperatures, we need to resolve, evaluate techniques spatially and temporally. John Jenks also looked at green roofs and cool roofs. Now these have been studied at individual building level. I think this is among the few studies that will do that at the level of an urban area. So cover all the roofs with more reflective material or with vegetation. And this is the change, the reduction in daytime temperature. So it's a little over a degree here for widespread use of cool roofs, and a little less than that for green roofs. So these are helpful to regulators in assessing if we go all out in any of these areas, what's the maximum impact we can expect from them. On the cool roofs, Jean-Jacques also looked at the slight increase in humidity, which works against thermal comfort, and found that on balance, the reduction in temperature outweighed the increase in humidity and gave us a net benefit, modest benefit in thermal comfort. Vegetation, we've used Eric and Matthias's flux tower to keep us honest on the latent heat flux and have improved the models of vegetation, particularly for trees. Without that, here are the data, Eric's data, and our models before Zhang Zhang and Liu Zhuan started on this were not very good, particularly in dry periods. And those models have gotten, the red solid line is our current models where we've done a much better job of accounting for the evaporative processes. Okay. I want to spend just a couple minutes on one technique we've looked at recently to tackle the anthropogenic heat. So we're not going to just turn off all the power plants in Singapore. What can we do? One aspect we looked at was in HVAC, an area that's where a lot of my work has gone. And the idea is this: a lot of the cooling in Singapore is used for dehumidification. No surprise for those of us who have spent any time here. And the process that we've done that by for 100 years, HVAC people, turns out to be pretty rotten. Take the Coke can out of the fridge and water condenses on it. This is what Willis Carrier did 100-some years ago. We condense water out of an airstream, and then we throw that cold water down the drain. The heat of condensation is quite high. So anybody who works in the desalination area would say that is really awful, about 2 orders of magnitude more awful than the thermodynamic minimum for producing water. And so we've picked up on some of that with our Sensum colleagues who have just recently started working on that. And this was a project that Well, here's one way of doing that, and that's to use membranes. Membranes can remove water vapor without condensing it, and so you get the benefit, well, you avoid the energy of condensation. And we came up with a system of doing this. This is 2 MIT grad students associated with SENSEM, one from Professor Lienhard's group who works on membranes for a living, and one from my group who works on buildings for a living. And they cooked up something where water vapor can be removed from a membrane here with the vacuum pump before it goes through a heat exchanger for cooling and into a building. And on the way out, it can be put again across a membrane into the airstream that's going out, which is at lower vapor pressure because it's been cooled. And this is something for which we filed a provisional patent, which is being prosecuted from the NUS service. And it has a COP of kind of, you get 10 units of cooling out of this, of dehumidification for every unit of electricity, which is really pretty good. Okay, let me come back to data for a couple of minutes here. This is the work of Tiangang Yin, whom Andrew mentioned. We've been waiting a long, long time for sort of high-quality data about the built environment in Singapore. Zhangjiang used some 5-6 years ago for his WRF model that took some effort to get, and it's now somewhat out of date. So where do we go? The government's still working on a virtual Singapore plan to make this available to agencies and eventually researchers, but we reached a point where it was holding up our work in various ways. So Tiangang went out and negotiated the purchase of a digital surface model from a Japanese firm. Here's the island, and you get all the surface features. This is 1 meter resolution. And from that, you can filter out all the large changes in slope that could be trees or buildings to get a digital terrain model that's shown here. So let's show you what we can do with this at the scale of the NUS campus, where there's some interest in having sort of a virtual campus model. Okay. Here's the digital surface model. Here's the digital terrain model after we've removed all the trees and the buildings. Okay. If we take the difference in those, we get heights of the objects, the trees and the buildings again at the 1 meter resolution. That's pretty good. We can now overlay with that the building footprints that come from the Singapore Land Authority or OpenStreetMap, and we can get our mitts on those data. The government doesn't hold them back from people like us. And so if you put that all together, then you get the heights of the buildings throughout the NUS campus. In terms of where we do our work, we're down here now some. Here's the Create Tower. Here are all the low-rise black and whites next to us and so on. So again, the resolution here is pretty good. We can extract the height, and then we can add that back onto the digital terrain model and get the overall heights of the buildings above, say, above sea level. Okay. So what do we do with that? Well, one thing we can do with that is classify all the land in Singapore. You know, we talk about urban heat island effect and say, oh, this is urban and this is rural. The profession's moved on from that. I mean, how dense is urban or rural? And so now there's a land surface local climate zone classification scheme for this sort of thing. And with our mapping and with Landsat satellite images in different bands, we have constructed a local climate zone map for all of Singapore, which will give us a sort of a world, a reference for our work that the rest, the global urban climate community understands. So this has the impact of vegetation and different building heights in it. And I've listed a bunch of other things we can do with this. It'll affect our mesoscale models. When we go down to microscale, we have better information about the buildings for our CFD models, energy balances, the sort of work that Megan will talk about on thermal comfort, and some work on estimating vegetation volume that we're starting to do with SEC. All of this builds on the data set that Tiangang has obtained and worked with. Okay, a couple more things. I want to show just mention two examples where we have combined data that we've obtained and built models on them. This one I'm not going to show in any detail, but here we wanted to understand better airflows in urban canyons under low wind conditions, where if one surface is hot and one is low, you can get a recirculation flow that can help transport pollutants out of the canyon. We didn't take measurements in a real canyon. That's kind of difficult. We made our own out of shipping containers on the NUS campus. Okay, 5 minutes, thank you. We visualized the flow with some theater fog. I won't give you the results of that, but we just have some very interesting correlations that allow us to predict this sort of thing. The other thing we did was look at airflow in void decks in Singapore. And real briefly, the idea here is how much airflow do you get under those? Singapore isn't doing as much of those in HDB. Do they have some value? So one of our students, Lukwai Chu, measured this in the civil engineering hydraulics lab near Ola Madsen's Monster. This shows the agreement of experimental data with a CFD analysis he did. This is sort of a blow-up of that. You get higher flow underneath here, particularly in the early ones. And then he built a 3D model of this so we could have with streets as well as canyons in between, sort of a 3D array. And interestingly, what we found and hadn't expected was that if you're moving along in the canyons, yes, if you have void decks, you get more flow than if you don't. But if you're in the streets, you also get a lot more flow than if you don't have void decks. And that's just due to overall reduction in flow resistance in the canyon. So this gives us some insights on say, urban design problems. Okay, just a couple more things here. The last 3 minutes. I'm going to zip through these, but the point here on all of them, and I'll skim, is who owns the models? Who gets to use them? Is it just researchers? Does it just go to government agencies? Or can we provide models that practitioners could use? And I'm very much an advocate of the latter, that innovations in urban areas are going to come from students, from architects, from engineers, from people in practice, as well as regulators. So in this one, this is a means of estimating urban temperatures with a nodal model and some representation of the simplified representation of the atmospheric processes. We've tested this with data in Singapore, again, Matthias Ross temperature data, and in European cities. The agreement's pretty good. The sort of thing we can do with this is also say, well, if it's hotter at night in an HDB area, how much does the energy used for air conditioning go up? And this is being incorporated in sort of open source tools for designers within the kind of CAD framework that designers use, the Rhino CAD program. And the tools are available on GitHub. And more about that in just a moment. We're doing the same thing for airflow. We have a simplified CFD code using Lattice-Boltzmann method. And the code itself isn't as important as just keeping the whole thing in the designer workflow. If someone's saying, how do I move buildings around? What if I do that? How does it affect airflow? Not having to go out to a CFD program, mesh it, run it, get the results, import them back and export them back into something. We speed up the process by being very careful about the wind profile we're using, and we get that from the sort of the density of the urban area. And very careful about minimizing the size of the simulation domain, so it's large but not too big, and relying on some theory from others to estimate that as a function of the size of the built environment. So here are the buildings. An architect could do this, and here are the results in a section and in a plan of airflows. This is the visual scripting language we do to glue these components together. And the very last one that Ken-Wee Chen, one of the workshop organizers, has done is at the urban level, okay? Maybe you have a topio sort of thing, or a spine, or a grid thing for an urban neighborhood. How do you mask the buildings? How do you vary the height for daylight, or PV, or to minimize solar heating on walls? And how do you run through a bunch of cases to try to pick out the best ones? He set up a selection of tools to do this, that start with various inputs from OpenStreetMaps or master plans, and then eventually producing a CityGML map of the same thing, and then something that might have PV energy or daylight availability. Okay. And the glue that holds all this together are his Python libraries, and then we can do an optimization that produces some sort of Pareto front of best case things. So this is also on GitHub, which in a way has become the an archival method of choice. We can put our code up here, and anyone in the world can access it. And they are using it in some of the cases. The Urban Weather Generator is getting a fair amount of use in this regard. So this is Kenmi's code to sort of glue all these other pieces together where models come from different code and then help the designer produce useful results. So with that, I thank you. As Janelle said, I can take a couple of questions while we're getting the next speaker hooked up, and otherwise I'm happy to talk in our panel session or the break or whenever you can get me. Thank you very much.